So I wanted to put together a video to discuss the definition of continuity. Uh, Continuity is an idea, or a function being continuous is a concept that you've spoken about in a past math class most likely, and what you've likely said is any graph that you can draw without lifting your pen or pencil from the page is continuous. But then when you get to calculus, you learn about limits and you learn that you have to kind of touch up some things that you'd previously discussed, and the idea of continuity is one of those things. So here's a definition from a calculus textbook of a function being continuous at a certain x value. So a function is continuous at x equals a when three conditions are met. The function has to be defined at a. When a function is discontinuous, this is usually the reason why, and this is what you would have been able to deal with in the past. But there are these other conditions as well, such as a limit existing. You are not continuous at a given x value if, when you approach that x value, the limit doesn't exist. This is something that you wouldn't have really been able to handle before calculus, as is this. If these first two conditions are both true, if the function's defined at a and the limit as you approach a exists, the last thing is that the limit has to equal the function value. If one of these three pieces isn't true, the function is going to be discontinuous at a. So from here on out, now that you know a little bit of calculus, if you're ever asked to justify why a function is discontinuous, the best way to do that is to figure out which of these three pieces of the definition of continuity is violated and use that as your justification. So these next few screens here, we'll just take a look at some different types of graphs and talk about specific types of discontinuities. This screen right here has two examples of what we would call point discontinuities or removable discontinuities. The reason why these are removable discontinuities is because what we can do with this function right here is we can redefine it at this one x value to include that point or fill in that open circle that's not included on the graph. So a removable discontinuity is a place on the function where you can basically fill in an open circle with a closed circle. Same thing is true over here. If I were able to redefine the function at this one location at the x value of a, and I would take this y value and move it down to fill in that open circle at this smaller y value, I would have redefined the function at a single location and I would have removed the discontinuity. These are the types of discontinuities that you really need to know calculus in order to handle. If you look at this particular function here, this function, the piece of the definition of continuity that's violated is that first piece, f of a is undefined. So that's why this function is discontinuous. What you will notice though is you will notice that the limit as x approaches a on this function exists. Okay? When you have a situation where your function's undefined but the limit exists, meaning you're approaching the same y value from both sides of the x that you're considering, you are going to be looking at a place where you have a removable discontinuity. You just have to fill in that one location where the function's undefined with a closed circle. With this function over here, again, we have the limit existing. That's the important thing to recognize about these removable discontinuities. When you have a removable discontinuity or a function that's discontinuous just at one point, the limit is going to exist and it's going to be a finite value as you approach that x from either side. Now in this case, f of a is also defined. So the first two pieces of the definition of continuity are definitely true, but the last piece, that f of a equals the limit, that's not true. The limit is the y value that's down here, the y value of this open circle, and then the function value at a is the y value of this closed circle. So the last piece of the definition of continuity is violated here, and that's that the limit as x approaches a on this graph is not equal to f of a. Talk more about removable discontinuities to conclude this video. A couple other types of discontinuities that you're going to have are jump discontinuities. These would be locations on piecewise graphs or maybe absolute value graphs where one piece of the function ends and then you jump up or down to another y value to allow the next piece of the function to begin. So these jump discontinuities are really going to be specific to absolute value graphs and piecewise graphs, which absolute value graphs essentially can be rewritten as piecewise graphs. But jump discontinuity is going to be a place where the limit as x approaches a on that function is not going to exist, does not exist. The limit does not exist. Right? If you approach on this graph, if you approach a from the smaller side, you get a y value that's down here. If you approach a from the bigger side, you get a y value that's different, a y value that's a little bit further up in the coordinate plane. And then the last type of discontinuity that we're going to really discuss in this video is going to be a vertical asymptote. It means your graph is either going up off the coordinate plane or down off the coordinate plane on either side of the x value that you're approaching. On a vertical asymptote, your function is going to be undefined. So if f of a is undefined, you're discontinuous. And when we have a vertical asymptote like this, f of a is definitely undefined. So we will wrap up this video by looking at two examples from out of a calculus textbook. The directions say to find the discontinuities for the function. For each discontinuity that's removable, define a new function that removes the discontinuity. If we look at number 13 first, if you rewrite this function with its denominator in factored form, it's going to be pretty easy to figure out what values of x make this function discontinuous. This function is discontinuous where the function is undefined, and this function is undefined when this is equal to 0, and that's when x equals -1, and when this equals 0, and that's when x equals 1. So this function has two discontinuities. They're at these two x's. The reason why is because the function is undefined there. Now if we were trying to figure out which of these discontinuities is removable, we'd have to figure out if the limit exists as we approach -1 and if the limit exists as we approach +1. Now if you think about the limit existing as you approach, we'll go with -1 first. If you're approaching -1 on this function, if you put -1 here and subtract 1, you're looking at -2 in the top, and then in the bottom you're looking at 0 times -2, so that's going to be 0. This is not an indeterminate form. This is going to give us an answer of either infinity or negative infinity, depending on which side of -1 we sit on. We're going to talk more about that when we learn a little bit more about vertical asymptotes in infinity. But this is not an indeterminate form. I'm just going to leave this as is right now and say this limit does not give me a finite y value. Therefore, this is a non-removable discontinuity at -1, but if I consider the limit as I approach 1, check out what happens. As you approach 1, which you can do because you're within a limit and you're not necessarily allowing x to equal 1, you're just approaching 1, you can't cancel these out if x equals 1. But if you're letting x approach 1, you're getting as close as you possibly can to 1 without actually getting there. This is never going to be 0 over 0. Therefore, we can go ahead and cancel those. So in the numerator, we're left with a 1. In our denominator, we're left with x plus 1. When we put 1 in place of that x and add 1 more to it, we get 1/2. What this tells us graphically is that on f, when we approach 1 from either side, our y value gets closer and closer to 1/2. We don't have a vertical asymptote at 1. We don't have a situation where we're going up off the coordinate plane or down off the coordinate plane on either side of 1. We have a situation where there's just a hole poked out of the graph at 1, since the function is undefined at 1, and this is going to be indicative of a removable discontinuity. How can you remove the discontinuity? Well, in this case, we've kind of got two options. One option would be to say, well, if I just rewrite the original function as 1 over x plus 1, my function is no longer undefined at that x value of 1. So if you rewrite the function for number 13 like this, actually let me call it a different name, let me call it g of x because it is a slightly different function. If you rewrite the function like this, 1 over x plus 1, what we ended up with within this limit right before we got the answer, this function does not equal f of x because f of x has a hole poked out of it at 1 comma 1/2, whereas g doesn't have that hole poked out of it because g is defined at 1. The other way to remove the discontinuity would be to say this. You can redefine it in a piecewise fashion, and you can say that it's going to be equal to the exact same thing. So x minus 1 over x squared minus 1 if x does not equal the place where we're trying to remove the discontinuity. And then what we can do is we can say if x equals 1, what we need to do is we need to fill in an open circle on our graph, a location we approach from both sides, but there's a hole poked out of the graph there. With the closed circle, the x-coordinate of that open circle has to be 1. The y-coordinate of that open circle has to be 1/2. So both of these functions would be ways to redefine the original function to remove the discontinuity at 1, but we can't remove the discontinuity at -1 because we'd have to totally redefine the function in order to achieve that. If you check out number 14 here, if we take a similar approach with number 14, if we write the denominator in a factored form, we want to figure out when the denominator is equal to 0 so that we can figure out when the function's undefined. When our function's undefined, we're going to be discontinuous. So if you're trying to factor this, I think you can go with a +2 and a -1. So when this factor is equal to 0, when x equals -2, our function's undefined. This factor is equal to 0 when x is equal to 1. Our function's also undefined at 1. We have two discontinuities for this function. In this case, if we're trying to consider whether or not either of these discontinuities is removable, we're going to want to check the limits as we approach these values. And if we get a finite value for the limit, we know we're going to be able to remove that discontinuity. That's what happened over here. We got a finite value as we approached 1, and we spoke about ways to remove that discontinuity. In number 14 here, that's not really going to be the case, because when you approach -2, the numerator is going to be -8, the denominator is going to be 0. This is not an indeterminate form. This is not 0 over 0. This is something that you'll eventually either be able to call infinity or negative infinity. And similarly, if we approach 1 on this function, we are going to get a 0 in the denominator again, but in the numerator we're looking at a 4, and that's not indeterminate. That is going to either be infinity or negative infinity. And like I've been saying, once we learn a little bit more about infinity and negative infinity and vertical asymptotes, we'll be able to finish these limits off and prove that we have vertical asymptotes at -2 and 1 and not holes poked out of graphs. So the important thing to recognize here about removable discontinuities, this is what you're looking to see happen. If your function's undefined at a given location, but you check the limit as you approach that x and you get a finite value, that's going to show you that you can remove the discontinuity, and you'd remove it using one of the methods that we explored down at the bottom of the screen here. Hopefully that's helped you come to understand a little bit about what exactly a removable discontinuity is and what signals it whenever you're checking limits.